Okay, team, welcome back. We're talking today the intro to solids. Okay, so this is the first lesson we're going to have in a series that I'm going to start working on that's going to take you through the solids course. Okay, so what do we call solids? Okay, at my university we call it solids. It's the class after statics. Okay, your school may call it strengths of materials. You may call it mechanics 2. You may call it mechanics of materials. That's the name of the textbook. Or you may call it deformable bodies. If your school calls it a different name, send me a note at the end of this, a comment, and tell me what your school calls this course. Okay. I'm going to teach this course. I'm going to use this book. This is the Hibbler book, the Mechanics of Materials book. This is edition 10. But it doesn't really matter what edition you have. 99% the material's all the same. Problems change a little bit, but this is the one that I'm going to be using, okay? So some of you may be using the Barry Johnston or the Philpott or whatever. Material's the same. Hopefully I can step you through this, okay? So one of the things that is going to be super important in this is our friend statics. Now, what happens when you get to solids is we expect you to automatically remember everything about statics. That's why I like to tell you to take this course right after the statics course, because it's still fresh on your mind and there's so much. If you take a problem like this, right, what would you know about that problem from statics? Well, the first thing in statics I would have asked you to find was tell me what the reactions are. So maybe there's a By, maybe there's an Ay, and maybe there's an Ax. In this case, Ax would be 0, right? Ax. So you could find their reactions. That was chapter 5 in the statics class. In solids, I'm going to think that you automatically know how to do that and you know how to solve for that. Take the moment at A, find By, do the sum of the force in the Y, find Ay, etc., etc., okay? You should be like an expert at that. What about a distributed load? What do you do with that? Well, remember, you turn that into a concentrated load right there. And it's 200 newtons per meter over 2 meters, so that would be 400 newtons. Okay? And then what else did we learn in statics that we could do to that? Well, we could draw shear moment diagrams, can't we? Okay, or you should be able to. And if you can't, you need to go back and review those videos. But I might ask you to find what's the normal force, the moment, the bending moment, and the shear force at any point in this beam. And you need to know how to do that. So this kind of problem needs to be automatic to you. If you're rusty on how to do any of the things that I'm talking about here, remember, I've got a whole series on statics that's 70 lessons long. You need to go back and review those. It's going to pay you big dividends to review that, because in solids, you can't do any of the solids material until you do the statics first. So you do the statics, and then you find out all the stresses and the strains. So speaking of that, solids is really going to tell us about stresses and strains and materials. This is the first, remember in statics, we had magic beams, didn't we? When we did this, did the beam ever bend? No. Did the beam ever elongate? No. When the temperature changed, did it get longer or shorter? No. We just ignored all that, right? It was kind of magic. Not anymore. Now in solids, we're going to say, okay, when you put these loads on a body, what happens to those bodies? Do they get shorter? Do they get longer? Do they deflect? Do they bend? What happens? Okay? And so we look at a couple of the material's properties. We look at stress, which has to do with the strength of the material. Stress is kind of like the concentration of the force. How's the material handle that force? What's the intensity of the force? Strain, on the other hand, it has to do with the deformation of the body. So strain is usually measured in inches per inch, and it's how much longer does the body get when I apply a load to it, right? We're talking about steel. You might think steel is super rigid, right? But really and truly it's elastic, because you can take the steel beam and you can bend it, and when you let go of it, it'll spring back, right? That's the elastic portion. Now if you bend it too much, if you get the stress too high, it bends and it never goes back, right? That's what we call the yield stress, and it never returns back to where it was, okay? So just as a quick introduction, as a reminder, let's run through one little problem here, okay? So we're going to talk about stress and strain and all that good stuff. The first thing we're going to talk about is stress. We'll talk about normal stress. It'll be the next lesson. then we'll move on to strain, and so on and so forth, and we'll step our way right through the book, okay? So let me erase this, and let's look at this right here right quick, okay? Let me erase that. Okay, let's look at this little problem right here. Okay, so I have a little simple beam, right? And I've got this little member here, member CD, holding it up. What is member CD? What's it called? Do you remember? Remember, it's pin connected at both ends. There's no force in the middle, so it must be what? A two-force member. Very good, okay? And it's got a distributed load on it, a triangular distributed load. Let's say that that's, I don't know, 1,000 pounds per foot, okay? So here's what I have, and they ask us to do this. Find the force in rod CD. So find out what's going here. The force in rod CD, is it going to be in tension or compression? What do you think? Well, if I've got a force pushing down on this trying to make that rod shorter, it's definitely in compression, right? So a compression, remember, when you squeeze me, I do what? I push back on you, right? So find the force in rod CD, find the normal shear and bending moment. Remember, every time you cut the beam, you must have an M and V, right? Remember my little rhyme? If you remember that, you won't have any trouble. And find that at point B, which is right here, okay? It's 2 feet from that hinge, okay? Let's see if we can solve this. So we're going to find this force, and we're going to find Mn and V at point B. Here we go, okay? Let's start off with, what's the statics? What do we start off with? Go. Free body diagrams, that's right. Okay, here we go. Let's draw a free body diagram. And the body that we want to free up, right, our free body, is this beam right here. And if you were that beam, what would you feel acting on you? Well, I feel a compression member that's pushing on me. That would be member CD, okay? We'll call him force in CD. I have a pin connection here. What's the reactions at a pin connection? Do you remember? X and Y, right? So X and Y. So we'll call that a Y. We'll call this a X. I'll come back and put arrows on that in a second. And then I have, of course, a distributed load, but I'm going to turn that into a concentrated load, right? And how big is that concentrated load? Well, it's 1/2 the base. The base is 3, right? From there to there is 3 times the height, which is 1,000. Okay, so what is that? 500 times 3 is 1,500, right? So this is 1,500, and where do we put the 1,500 on a distributed load? At the centroid. Hey, that's a statics thing too, isn't it? Okay, and remember where the centroid of the triangle is? 1/3 from the fat end of the triangle, right? So that's 1/3 here. And the whole triangle is 3, so this must be 1 foot away, right? So let's put that on our free body. We'll put this here, and this is at 1 foot. This is 1,500 pounds. What's this angle here, y'all? What about that angle? Let's see, the beam this way is 2, 4, 5, and the beam this way is 5. Hey, if I have a triangle that's 5 and 5, what's the angle here? 45 degrees. You remember. Okay. Let's see. What do you think? Which way does AX have to go? Since this guy goes that way, AX needs to go that way, right? So AX like that. And then AY, I think AY has to go up, don't y'all? Okay. How do I know that? If I take the moment here in my brain, what gets knocked out? This gets knocked out, and that gets knocked out, right? Because it's a cha-cha force that goes through. So this rotates me this way, so that has to rotate me the other way, right? There you go. So, how do I solve for FCD? That's the first thing they asked me to find, the force in rod CD. How do I find that? Piece of cake from statics, right? You just take the moment at point A. Okay, there's our little thing to tell us that that's positive, right? Counterclockwise is positive. So here we go. I've got 1,500 rotating me clockwise, so minus 1,500 times how far away? Well, 1. And then this guy over here has 2 components, right? This component here goes through point A, so that's a cha-cha for us. He's knocked out. This is the one I'm asking about, so if I take it at point A, this guy makes me rotate. Which way is that? Counterclockwise is positive, so plus F CD sine of 45, right? This is sine of 45, that's cosine of 45, times how far away? How far is that from point A? Well, it's 2, 3, 4, 5. Okay? And so now I can solve for FCD. Uh-oh, I need my calculator. My handy dandy calculator. And if y'all don't have one, I highly recommend a TI-36 Pro. This calculator is okie bueno. Okay? So here we go. I got 1,500 divided by 5 equals divided by 0.707 equals 424.34. 424 point, let's just call it 3. Okay, and that's pounds. Yeah, and in the other videos you see me with a different calculator. That's because the students keep stealing this one from me. Bring my calculators back. Okay, so now I know FCD. Let's see, we need to find AX and AY. Okay, well that's pretty easy to do, isn't it? If I just sum the forces in the X, what do I have in the X? I have minus AX plus that guy, which is FCD cos 45. So let's see, that number times 0.707 equals 300. AX equals 300 pounds. How about the sum of the forces in the Y? What do I have in the Y? I have AY minus 1,500 plus FCD sine 45. Well, that's the same as that up there, isn't it? Since cosine and sine are the same, so that must be 300. So move that to the other side. Subtract 300 from it. AY equals 1,200 pounds. No calculator. What? Okay. Make sure that old Dr. Hanson doesn't make a mistake there. 300. Yeah, that's right, isn't it? Okay, here we go. So what do we know? We know FCD. You're 424.3. And we know AY is 1,200. And we know AX is 300. Now that is statics 101, isn't it? Okay. We did a moment equation, and then we did sum of the forces X and sum of the forces Y. God, we know how to do that, don't we? Okay, so now let's go back and let's do one more thing. Let's find what the normal force, the shear force, and the bending moment are at point B. All right, do you remember how to do that? Well, to find out what's going on inside the beam, you simply need to cut the beam at point B, right? So we're going to slice the beam at point B. Well, here's point B right here, let's say. Okay, so I'm going to slice through right there. Now I can draw this side or I can draw that side. It makes no difference, okay? So let's see. What are we going to draw? You know what I think it's easier to do? I don't even know. I think it's not too bad either way. There goes my lid. Let's draw that side, okay? All right, so I'm going to erase. What should I erase? I'm going to erase this. Now remember, there is a distributed load here, okay? I have to leave that alone. Let's just draw it over there, okay? So here's what I'm going to draw. Okay, so here's where I cut it. I cut it right here at point B, right? Here's point B. And when I cut it, remember I still have this distributed load on this side of the beam here, okay? My pen is running out of ink. Okay, And this is 1,000 pounds per foot. What about at B right here? Now remember, look, this is what? This is a third, and that's a third, and that's a third. So if I started at 1,000, this is 666, 333, 0, right? Similar triangles would tell you that also, okay? That should be a review for you. So where I cut it at B, the height is what? 333, right? At 666 there, 333 there. So this is 333.3 pounds per foot, okay? Now, I also know that I have this reaction force over here that is 1,200 pounds, okay? And I have this AX that we found was 300 pounds also, right? 300 pounds, okay? Now, what happens where I cut the beam? Remember, every time you cut the beam, you must have a MNV. Okay, so here you go. If you can't remember that, we got trouble, right? Here's your N, here's your V, and there is your M. Remember, this is the positive sign convention when I draw the left side of the beam. If I drew the right side of the beam, all these forces would be opposite direction, okay? So here we go. Let's take this distributed load and let's just divide it into a triangle on top of a rectangle, okay? So there's the rectangular portion and there's the triangular portion at a third of the base, right? So how big is the rectangle? Remember, this is, where did we cut it? We cut it at 2 feet, right? 2 feet. So the rectangle is 2 times 333.3, which is 666.67. And then it's 1,000 at this end over here, right? So what's this height here? Well, this height here is 666.67, right? So the area of the triangle must be 1/2 the base times the height, right? So this over here also 666.67 at a third, right? Okay, here we go. Let's find N first. That seems very easy to do. It's in the X direction, so let's just sum the forces in the X. And what do we have? We have N, and we have minus 300 pounds, and that's all there is to it. So N must be equal to 300 pounds. That was easy. All right, so let's see. We found the force in the rod CD, that's there. We found N, that's there. Let's see if we can find shear force, right? That's V, remember the scissors for shear. Sum of the forces in the Y direction equals to 0 equals, what do I have? I have 1,200 going up. I've got a minus V. I've got a minus 666.66. But I've got 2 of those, right? I've got 1 there and 1 there. So let's just put a twodoms on that and multiply it by 2. So let's move the V to the other side. What does handy dandy calculator say? It says that V must be equal to, we'll move the V to the other side, so V equals 1,200 minus 666.67 times 2 is negative 133.34 pounds, okay? Now, what does that negative tell me? Remember, I just drew this according to the positive sign convention. These are assumed directions. So we assumed V to be going down. Which way is V actually? V is actually going up, isn't it? That sign right there tells me that it's opposite of my free body diagram, okay? Last one, and that is we got to find that guy. Because we found that guy, right? V. So here we go. Sum of the moments, and let's do it about point B, where we cut the beam. Okay? All right, so what do I have if I take the moments there? Well, I don't knock out moments. I knock out N and V, but I don't knock out M, so that's positive M. And then I've got the 1200 over here that rotates me negative. So minus 1200 times how far away? 2. And then both of these guys rotate me positive, right? So plus 666.67 times, okay, how far away is that one? Well, it's half of 2, right? The rectangle's right in the middle, so that's a 1. And then plus 666.67 times that one. How far away is that one from here? Well, if this is a third of the base, this must be 2/3 the base. So what is that? 2/3 times 2 is 4/3. 4 divided by 3, I know what that is, 1.33. 133. That's what happens when you get tired and at the end of the day you can't add anymore. So let's see what M is equal to here. M is equal to 2400 minus 666.67 plus 666.67. That's not a plus. That's a minus. No, it's a plus and a plus. They both rotate me counterclockwise, right? Oh, so that means I have to go back and change my sign. Oh, I'll put it on the other side. Never mind. See, I'm doing too many steps in my head, y'all. 666.67 times 1.33. Yeah, I'm moving this to the other side, so that's going to be positive, and these two are going to be negative, right? Is 846. 846 point, oh, say 0.7, and that is foot-pounds. Okay, so that is the bending moment at point B. Okay, so we found that also. All right, so I think that's everything we asked for. So this is a basic review of things that you ought to recall from statics. If you're having trouble with anything I did here today, what do you need to do? You need to go back and review those statics lessons, right? Because what we're going to do next is, what's the stress in this bar? Well, the stress depends on how much force is in the bar divided by how much its cross-sectional area is. And if you can't calculate the force in the bar, you'll never get to the stress, right? So if you can't do the statics, you'll never get to the solid stuff. So early on in the game, lesson 1, do yourself a favor. If you're weak at this, go back and review those statics videos, okay? I know they'll help you. All right, next time when we start, we're going to get into solids. We're going to be talking about normal stress. See you later.